full screen. Now, did I do something like number 7 last time? I don't remember. Where it was on a plane. It was at an angle.
No.
Are you sure? I thought I did.
Oh yeah, but it has a number involved, unlike this one.
Well, let's see how we do. So in number 7 we have an object of mass m a body slides with constant velocity down a plane inclined at 30 degrees to the horizontal, showing a diagram of the forces acting on the body, and find the coefficient of kinetic friction, that's just friction, between the body and the plane. Okay, so what you have here, if you want to draw, this angle here is 30 degrees. And then you have a mass here, m. Now, what force is on m here? The weight, yeah, very good. So what's the weight here? mg. Now, you should resolve into this one and into this one. Who knows what this angle is here? 30. So therefore, this is mg cos or sine? Cos 30. And then this one here, mg sine 30. Now, is that all the forces?
Friction.
Friction. So there's a friction force here. Friction. Is that all the forces? Very good. And then there's a reaction force here, isn't there? Now, you have a formula for friction, though. What's the formula for friction? I gave it to you? Very good. It's mu r. And they are looking for the mu. That's what they want, is the mu.
Is that number 7?
Yes.
Okay.
So, I can make some equations here.
Yeah. So how do I know that they're looking for mu?
That's called the coefficient of friction. Now, we know the R equals the mg cos 30. Okay? Because, if you look at the picture, is the block going up and down here? No, it's not. Look again. The box is not doing this. What's it doing? It's doing this. So the force here must equal the force here. They must. So we know that R must equal mg cos 30. Now what's a little more difficult though, we know that mg sine 30 must equal mu r. But my question is why?
Because
You see, it's not
the two sides, it's there from the right and the left, it's...
Yeah, but why is it equal?
It should be greater than...
Yeah, you think this one, it's moving this way, isn't it?
Yeah.
So you think mg sine 30 should be bigger than mu r? Yes? No.
No.
Now, wait. Newton's first law. Just listen. Newton's first law. A body at rest will stay at rest unless a force acts on it. Or a body in constant velocity will stay at constant velocity unless a force acts. So if you read the question, it says it's moving at a constant speed, is not accelerating. If it's not accelerating, then the total force is zero. It's balanced.
So in constant velocity, the acceleration is 0.
Yes. Okay. So because it's constant, there's no force.
What if it says it's in a constant acceleration?
Oh, well then
Is there
it's
a
not
velocity?
balanced.
Is there a velocity if there's a constant?
Oh yes. Yes. For sure.
The question says it's moving at a constant velocity.
Yes. And that constant velocity. Come on, why are you late, Joshua? Come on, hurry up. Yes, because it's at constant velocity, it means the force must total 0. So this one equals this one. Yeah? Hey, come on. What's wrong? Dana soon? Dana and soon? Is that okay?
Yes.
Yes? And everybody else?
Yeah.
Yeah. So now, so the reason why is from Newton's first law, N1 I'll call it. Now, can we work out the mu now? Did they give us any more information?
We don't need anything else.
Probably cancels, does it? Okay. So here, I get mu equals mg sine 30 over r. That's from this equation. But what does r equal?
Mg cos 30.
Yeah, mg cos 30, isn't it? So you can just type this in on the calculator because they cancel.
Root 3 over 3.
Root 3
Over 3.
over 3. Okay, and what's that as a decimal?
0.
5/8, yeah? Oh, sorry, let me pull the blinds down a bit.
Why is it always so?
Yeah, it's like it moved a little bit. It just needs to be moved to the right. So was the complicated part of the mg sine 30 equals mu r, or was there something else that was complicating?
I don't know. When you read the task,
No,
I
I-
realized what you did.
Yeah, it's easy when you see
Everything
it.
in your voice.
Makes it easier.
I didn't understand when it says coefficient of friction.
Oh, well, so the question would be the first problem, yes. Yeah, anything else that was a problem?
So what if I took, what if I make it in this way? Mu r, if I make this as equation 1 and equation 2,
Yeah.
and I divide it still the same.
Oh, as a division, yeah. Yes. That would
Because
do it.
after-
Yeah, because you also cancel
Are
that,
we
yeah.
going to do the second part of the question?
Well, is the second part kind of just the same idea, or is there something different to it? Let's have a look. If the plane was now 60 degrees with the horizontal, with what acceleration? Okay, so now it's 60 degrees, what's the acceleration? So no longer constant velocity. So let's have a look. Can I scroll down? Yep. Oh, well, I need to go back to this for the information. So now it's 60 degrees. Okay. So if you remember, I'll draw it in red. Which one was cos and sine? Was this the cos one?
Yeah.
It was, wasn't it? Mg cos 30, and then this one here, mg sine 30.
So it's not 30 now, it's 60 now.
Oh yeah, thanks. Yeah. And then this one here, mg sine 60, and this here is still r, and then this one here is mu r. Now we know what the mu is. What is it? 0.58 r. Okay. Now, please note, mg sine 60 is not 0.58 r anymore because
Acceleration.
it is accelerating now. It's accelerating.
So mg sine 60 minus
Very good. So we can use the total force would be mg sine 60 minus 0.58. Remember, it's a bit like my rocket example. Remember the rocket I did? It's the force that drives it minus the force that drags, that resists. Okay? Now,
and that's equivalent to resultant force.
yes, very good. It's called the resultant force. Oh, and I actually know what the R is as well. I do know what R equals. What does R equal? Mg cos 60. Okay, so I can say This is mg sine 60 minus 0.58 mg cos 60. But from Newton's second law, what does F equal? ma. Now what's in common to all of these? Mass. Can you see that? M's go. So I'm left with A, that's what I want, equals G sine 60 minus 0.58 G cos 60. Now does it say G is 10 or 9.8?
Yes, 10.
No.
It's 10.
Yeah, 10.
The beginning of a page, the previous page.
Yeah, 10.
Does it say 10 for all the questions?
Yes.
Okay, cool. So it's 10. So what do we get for A?
5.8.
5.8 meters per second squared.
Is this the same question?
Second half of it, yeah.
It's 8 point
What's that?
6 for the first one.
5.86. Yeah, okay.
What force applied parallel to this plane would be?
Oh, there's another part.
Yeah.
What force applied parallel to this plane would be required to cause the body to move up the plane? Okay, I think I'll not do the last part. The last, I'll just talk about it. You can maybe figure it out yourself. So the last part is they would like to know how much force should you push here so that instead of falling, the block goes up. Okay? Well, maybe I will do it. In this situation, what you would need is F.
Push or pull?
I think it's a push. Well, sorry, it doesn't matter really. Just upward force. Yeah. F plus 0.58 or needs to be bigger than mg sine 60. This is part 3 of the question. And this was part 2. So that means you need F to be bigger than mg sine 60 minus 0.58 or. But we know what or is. What is or? Yeah, it's mg 0.58 mg cos 60. So, sorry, it's getting a bit messy here. F needs to be bigger than mg, bracket. Now, can someone type in sine 60 minus 0.58? Yeah, sine 60 minus 0.58 cos 60.
0.578.
0.578. So
0.58.
So we'll just say 0.6.
Is this
It's like 5.8.
it's the same as acceleration?
Oh, okay. Well, that's I think just an accident. We'll just say, okay,
Same way.
that's fine. That's fine. So if you apply a force greater than 0.58 mg, what would happen? It would move up because this together we said we wanted to be bigger than this. Rats. Sorry, I realised I made a mistake here. It's well, maybe someone can tell me my mistake.
You just said
No. What was my mistake? If the block is going up, what has happened to the friction? It's going down. So when the block is going up, that one is this way. So you see here, that should be a minus. So that should be a plus, that should be a plus, that should be a plus. Okay, so what is it now with a plus? Because friction always is against the motion. It's always backwards. Friction can never help you go up the wedge. What is it? 1.16 mg. Okay. See, that's exactly the thing that would happen in the exam. You know, and the mistake I just made there, this is where you need to be concentrating and just, you know, before you finish the question, just think if that makes sense. And when I was thinking about this, you know, when I was circling, I realised, oh, that's friction. So it's the other way. Okay, these things happen. Do we have the answers at the back? What chapter number is it at the back? Statics and dynamics
So
number.
we just have to leave it as mg in the form of mg.
Yeah, because we don't know mg. Yeah. Oh, but we do know g, don't we? So we can say f must be greater than 11.6 m. Yeah. What number was that now? 7.
First part is correct.
Yeah. Can someone type? Yeah.
Second part is correct.
Can someone type in 2 root 3 divided by 3? What's that? I hope it's 1.16.
1.15.
Yeah, well, close enough. Yeah, yeah. So all those answers are right now. Okay. I think they left it like this at the back, except they didn't put the decimal in. So you can leave it like this. You don't need to write that down.
But that is fine.
In the exam, perfectly acceptable. Yes, yes. You don't. You can leave it as decimal. Yeah, yeah. Okay. That was a good question. I really feel like this is, you know, exactly the type of question you would see in the exam. So that's a good question now. Okay. What one's next? 8. Oh, that's with the lift, isn't it? Okay. Can I scroll down? Not yet? Is that yes?
Yes. Wait.
Just wait a minute, okay. I'll read number 8. An object of mass m rests on the floor of a lift, which is ascending with acceleration a. Draw a diagram to show the external forces acting on the object and write down its equation of motion. How do these forces arise? Show graphically how the magnitudes vary with the acceleration of the lift. What force constitutes the second member of the action? Okay. Very, very long question with a lot of descriptions in it. I'll just talk about number 8. It's the idea that they want you to understand in 8. So I'm going to scroll down now. Whoa. Okay. So here we have is a lift, and it's accelerating with acceleration of a. Okay, and then inside the lift we have a mass of m. What is the acceleration of this mass? Is it the same, more or less than a? It is also a, as long as it's on the floor.
Yeah.
So this is also going up with a. So the mass is going up with a and the lift is going up with a. Now let's look at this mass.
Here's the way.
Yeah, here's the mass here. Now I don't want to get all Matrix on you and, you know, imagine you are the spoon. You remember that line from the Matrix movie, don't you? You all seen the Matrix, haven't you?
Yeah.
I don't know if it's too old now. Long time ago, yeah.
So old.
Yeah. There was a line in it when he's talking to the little Indian kid in the apartment with the spoon, yeah. And he says, I think he says, eat the spoon or imagine you're the spoon or something. So I want you to imagine you're the mass. Okay? So if you are this mass, what forces do you feel? Let's try to be specific. Yeah, so gravity, you feel pulling you down.
Yeah.
So for sure you have gravity. mg. Now what else do you have?
Reaction.
Very good. Reaction. Yes? No friction unless it's sliding, so we won't assume it's sliding. That's it. No, that's it. That's it. Yeah, no left or right here.
So it's R minus R.
One sec, yeah? No. Because if you are the mass, you don't even know that the lift exists. all you feel is a force underneath pushing up, which is the reaction, and this earth thing pulling you down. But everything outside, not in contact with you, you don't experience or know about. Okay, the block only feels what's in contact with it. Now, your point is something that does cause confusion because it's inside the lift and the lift is going up with a force. Okay, but like I said, imagine you're the mass. You only feel two forces. Okay. Now, what is the total force here? No, not zero.
R minus mg
Very good. R minus mg.
equals to ma.
Yeah, and Newton's law says this is ma. Now, I think what they're looking for in this is they would like the reaction, really. So,
Isn't that the equation?
oh yeah, sorry. So this is answer part 1. They wanted the equation, wasn't it?
No, part 1 they wanted just a sketch.
Oh, sorry. So that's part 1. This is part 2. And what else then? Draw a diagram. Write down the equation. How do these forces arise? Well, we talked about that. Show graphically how their magnitudes vary with the acceleration of the lift. Okay, we'll just do that part.
How do these forces arise?
Yeah, what I'm going to do is just work out what R equals. What does R equal? It's MA plus mg. Now let's draw a little diagram here. Okay. So if the lift is not accelerating, what's A? 0. So what is the reaction? No? Is mg. Now that makes sense, doesn't it? If the lift is not accelerating and I just have the block on the table, what's the reaction? Equal mg. Now what happens when A gets bigger? What happens to the reaction? It gets bigger, so the graph goes up. Now just really think about that. Imagine if you're in an elevator, in a lift, and it starts to move up. You feel heavier, yeah? Because the floor is pushing up more. As the lift accelerates, more and more acceleration, you can feel that pushing up. But then, when the lift goes down, you feel lighter, so your reaction is smaller. So if A is negative, which means it's going down, what happens to the reaction? It gets smaller. So it'll go this way.
And at some point it goes just...
Yeah, and at some point the reaction is 0. What would that mean if the reaction is 0?
Acceleration.
Your weight is 0.
Reaction is equivalent to the weight. You don't feel anything.
Yeah, if yes, pretty much. If the reaction is 0, it means you're no longer touching the ground, which means you're just kind of floating. Is that possible? Yes. When?
If the lift is going fast and stops.
Oh no, much worse than that.
They just
Free fall. Somebody cuts the cable and then the lift falls. Reaction becomes 0. So now there's no more reaction. So you're not even touching the ground.
No, the same would be if the lift is going up fast and it stops. So you will feel it for a short period of time.
Yeah, that's a different principle. Yes, it's true. I was more thinking about continuously. Yeah. So as the lift is free falling. Yeah. Okay. That's number 8. Yeah. Okay.
But what force constitutes the second member of the action-reaction pair in the case of each of these external forces?
Well, how much do they want you to talk about this at the back? Because I think I just want to get the ideas across here. Number 8 isn't even at the back. I've said enough about it. If you really want some answer, let's see. What force constitutes the second member of the action-reaction pair in the case of each of these external forces?
I just didn't understand what you're doing.
I don't know what they're talking about. What force constitutes the second member of the action-reaction pair in the case of each of these external forces? That's almost a sentence. I really don't know what they're asking. There's only two forces. What are they? Reaction and weight. They might want you to talk a little bit about the reaction, but I don't think that's what they want. But that reaction is from the lift, and the lift is moving. And what force makes the lift move? No. How does this lift move up? Because there's a force here. Yeah. So if you were the lift, imagine you're the lift, what forces do you feel?
Weight.
T, and then a big weight, isn't it? And then there's another force. Reaction. Yes. Which way? Up or down? Not down.
Because you're moving up.
Now if you think about it, if I push against the wall and I feel a reaction this way, and then imagine I'm the wall, and someone pushes me, I push out that way. So it's the same here. For the lift, the oar is the same, but the other way. Okay? So likewise, if I push here, which way is the reaction? Out. And then if I am the wall, the reaction is now, no, the other way, isn't it? Sorry, it's that way. Yeah, that's weird. It's this way. Yes. Oh, don't think about that too much. The reaction's always opposite. Okay? So if I push here, I feel or going this way. And then if I'm the wall, if I'm the wall, I feel a person pushing this way with or. Yeah. Yeah. I push, I feel or this way. Then the wall feels me pushing that way with or. And no reaction. Oh, but yeah, the reaction that way, yeah. The cancel to make 0. Okay, that's enough about that one. So that's 7 and 8 then. So we'll go continue where we left off, which is... What? What were we talking about? 9. No, I mean the notes. Where did we stop?
We finished with 3 laws and we solved...
We did the 3 laws.
We solved one question.
And we did the rocket, wasn't it?
Yeah,
yeah, okay. Right.
What is the usual?
So, I think we have F equals MA. Yes. And now we're just a little bit of vocabulary before we start the new topic. Oops.
So
Okay.
what is the new topic?
Momentum. But just before we start momentum, some vocabulary. So this is just vocabulary.
Now studying momentum.
We'll do,
Now studying new lesson momentum.
momentum in a moment. I just need to give you this vocabulary. So, when an object falls to the ground, this force is mg, and then what's this force?
Yeah.
No, it's falling. It's in the air.
Oh, this is 0.
Well, no. It's friction from the air.
Okay, yeah.
Air friction. Air friction.
So, can you repeat that?
Yeah, this is falling. So there's mg down and air friction up. Now, which do you think is bigger?
MG.
Mg is bigger, isn't it, than the friction? But the thing about air friction is this. As this gets faster, does the air friction get bigger or smaller? It gets bigger. Okay? Because the way air friction works is that the faster you're going, the more force you feel. Now, if you just think about that, does anybody cycle?
Yeah.
Yeah, if you cycle, the faster you cycle, the more air friction you feel. Yeah? And it's the same when you drive a car. The faster you drive, the more air friction you feel. So at some point, at some point you have this situation. Friction equals mg.
Is that the reason for heat when rockets come back to Earth?
This will be the reason when you have parachute jumpers. They don't keep accelerating. They reach a maximum speed and then they stay at that speed. So they stop accelerating. That'd be the main reason. I'll show you this in a graph. So, the heck. Okay. So here, this is time and this is velocity. Okay. Now, somebody jumps out of a plane. So what's their velocity? It's 0. And then as they fall from the plane, do they get faster or slower? Well, they get faster. But they don't keep getting faster. At some point, they stop accelerating and they go at a constant speed until they hit the ground and they are dead. So I'll just put it there. Okay? This speed here is called terminal velocity. It's really the maximum speed. And the reason for it is because the friction equals the weight.
Sir, could you repeat the graph, please?
Yeah, so this person, here, we'll put them in a helicopter. And they jump out. And as they fall, they get faster and faster. But at some point, they reach a maximum speed. And they just keep at that speed until they hit the ground.
How is that?
Because the air friction equals their weight. There's no more total, the total force is now 0. If the total force is 0, they travel at constant velocity.
So there is no force that's pushing them down, and there is no force that can lift them.
Yeah, the force is balance.
When there is no force, there is no acceleration.
What's Newton's first law?
Body at rest will stay at rest.
Yeah.
It says force action.
Yeah, and then the other version,
Body at constant acceleration, constant
velocity, yeah.
Stay at constant velocity until another force is active.
So that's what's happened here. He is now at constant velocity because his weight equals his friction. Yes?
Is it the same as terminal velocity?
Yeah, terminal velocity is a constant velocity. It's your maximum velocity. Is this idea difficult or is there questions on it? It's okay? What? No, seriously. Do you have any questions on it or is it okay?
What makes the friction equivalent to the weight?
Well, what's happening is as he falls, he gets faster, true? As he gets faster, what happens to air friction?
Friction
It gets bigger and it will increase until it equals the weight.
How do I define terminal velocity?
Yeah, if you want a formal definition, you would say terminal velocity is the maximum velocity normally in free fall. Yes. Yes. Make sure you come back though. Okay, did you write that down? Yeah?
So when a guy jumps off a helicopter, he'll probably go faster and faster to a point where he reaches terminal
Yes,
velocity.
that's exactly what happens.
He turns into a free fall. I mean, he goes to free fall.
He's in free fall and then he's in constant velocity.
Cars attain terminal velocity.
What's that?
Cars can do it.
Yes. I said it's normally for free fall, but it's the same idea in cars. The reason a car has a maximum speed is because the force of the engine will equal the air friction force. Okay? So the same reason cars have a maximum speed is because of air friction also. So if you put your car in a tunnel that has no air, it would go much, much faster.
So, but this doesn't apply when you're in a vacuum, right?
What's that?
This does not apply if you're in a vacuum.
No, you're right. It does not apply in that situation. Yeah. Okay, I'm going to scroll down now, okay? So now we can start our next topic. So what we're going to look at here, we talked a little bit about this the last time. Momentum. Yeah, do you remember when did I use the word momentum last time? I used it in the definition of force, wasn't it?
Yeah.
What did I say it was? It is the rate of change in momentum, yeah. And I gave you the formula for momentum. What was it? Yeah. Momentum. What letter is momentum? No.
PV.
P.
P, sir.
Yeah, sorry, for momentum. And the formula is mass multiply velocity. Yeah, okay, good. So in fact, you have this formula I gave you last time. mv minus mu over t, which is the same as ma. Oh yeah, and then there's another one too as well. Okay. Yeah. Now, that's good. We can take this formula here and rewrite it. We can change this into Ft equals mv minus mu. And this is actually a new formula. Oh good, you know this word. New formula. mv minus mu. Somebody describe in words what does that mean?
Change in momentum.
Yeah, this is the change in momentum. And that has a special name in physics. We call the change in momentum the impulse, which is I. So we have two formulas for I. This is the definition, and then we have from here this formula. So we have two formulas for I.
It could also be Ft equals to mv minus mu.
Yeah, you can put them together like that. I'm going to leave them separate like this. We have that formula or this formula. So why do we have two formulas? Well, it depends on what information we know. So for example, let's take this here. I know the mass, yeah? And let's say I know it's u. So let's just imagine it's moving along here with speed u. Okay? And then maybe I hit it, and now its speed is v. So you know the m, the u, and the v, so you can use the first formula. Okay? Now, again, this is moving along with m. Okay? But this time, I know the force and the time I use the force. Example, 6 newtons for 2 seconds. 1, 2.
So it's the other formula.
So it's that formula. So it depends on what information you know. If you know the velocities, you can use the first formula. But if you know the force that changes the velocity and the time, then you can use that. Okay? So the situation is the same. Same situation, it's just different information. Now this time here has a special name. Does anyone know its special name this time? It's called contact time. I'll write that down. Contact time, because it's the time when you touch. Contact. Contact time. Let's see. So this is called oh come on. That one's called contact time. Yes. Let's do some. I just want to do a small example here with impulse, although I think I might have. Weird. Okay. let's do a small example with impulse, an example that I like. Can I scroll down? Yeah. Okay. So let's take example here. So here is that's Mo, okay, and that's me, and then Mo is late for class again. So then I push him and he falls. Yeah. I will change the story. So this person here jumps to the ground. So let's say the height here, let's just say it's...
100 meters.
No. Let's make it smaller. Let's just say 4 meters. Okay. So what is the velocity at the top?
0.
U equals 0. What's the V here? Well, let's calculate it. Let's just say G equals 10. So what formula could I use? Well, I think I would need to use V squared equals U squared plus 2AS. So V squared equals 0. What's 2A? 20 multiply 4, 80. So, yeah, what's square root of 80, please?
It's 8.9.
8.9?
Yeah.
Okay, meters per second. Right. So, if you think about it, yeah, I'm going to take down as positive and up as negative for this picture. Okay. No, that's okay. You're right.
But do you have to write the ones that are for positive?
It's helpful if you do. Yeah.
But in this case, the U and V is in the same direction. So why is that should be a negative or positive?
Huh? No, I'm saying down is positive.
Yeah, so it's both is positive.
Both positive, yeah. Now, look here. Now let's look at this problem. Okay? So, just before he hits the ground, what's his velocity? 8.9 meters per second. And then when he hits the ground, 0. Now, what's his mass? What mass will we give him? 50? Okay, 50 kg. And here's 50 kg. Okay. So, just before he hits the ground, this is his speed, and then after he hits the ground, this is his speed 0. So let's work out the impulse. It's mv minus mu. Can you tell me what that is, please?
It's 445. Negative 445.
Negative 445. Oh, what's the unit, by the way? Well, we can see the unit here. It would be Newton seconds. It will be one way, yeah.
So can I put like kg/ms?
Yeah, you could do that too. Newton seconds. Now, when he hits the ground, he feels the ground pushing up with a reaction force. And this force stops him, right?
Yeah.
He's falling and he hits the ground and he doesn't continue. He stops because the ground pushes up. Let's work out that force.
So what is the negative indicate?
The impulse is up. In other words, there was something going up that took his momentum. Okay, do we have another formula with force in it for impulse? We do.
FP.
I equals Ft. So what does F equal? I over T. Now we know the I. What is the I?
445.
Yeah, minus 445 over T. Now what's the T here? What's the T? No, but what does it represent? Yeah, so in this situation, yeah, that T is how long he is
He hits
in,
the ground.
yeah, it's his time he's in contact with the ground that's slowing him down. So for example, it's the time it takes for him to slow down and stop, to bend his knees. This is the contact time. Okay? Now this is the point I'm trying to make. Let's say the contact time is 1 second. So he lands and stops in 1 second. what's his force he feels on his legs?
Minus 400.
Minus 445. So it is like he feels 445 newtons
Goes
up.
against it.
Goes against him, exactly right. But if his contact time is 2 seconds,
So it's divided by 2.
divide by 2.
Yeah, that's much more.
It's smaller, isn't it?
So it's
So
2 to 2.5.
2 newtons about. So my point I'm making here is that,
The larger the contact,
yes,
smaller the force.
that's it, that's it. The larger the contact time, the smaller the force he feels on the ground. Yeah, you can think about it 2 ways. It's the time he spends in contact with the ground that is slowing him down. You know, because obviously, yeah, his foot has touched the ground and he's decelerating until he's now at rest. Yes. Or another way to describe contact time is just the time spent decelerating. So it'll be a small number because he'll very quickly come to rest. Okay. Now you can see my point I'm making here is there's a big difference between 1 second and 2 second contact time. Okay. So this is why you know if you fall to the ground, what do you do with your knees when you fall?
You bend down.
You bend them. And the more you bend,
So increase the contact time.
the bigger the contact time,
So the less
the less the force on the legs. Okay? Same logic. When football players kick a football, you want to try and increase the contact time.
So let's increase this contact.
No, because it's a different diagram, different situation then. The contact time can increase or decrease the force.
Yeah, because football players want to kick the ball.
Yeah, so you think about a football player. What's the force? The force is, the muscles in his foot. Yeah? So we can use the formula I equals Ft. So the F he can't change because that's the force in his foot. The T he can make bigger.
Yeah.
So it is a slightly different situation. Anyways, here you want to make contact time big. As a footballer would want to, small. No,
So it's
big. Contact time big, yeah. And a football player would want to make contact time big as well. You get this question in the exam. What happens in the exam is like this. They would give you the U, and they would give you the V, and then they would ask you for the force. Or they would ask you for the time. So let's pretend they ask you for the force, they need to give you the time. So, how long do you feel is a good time? When you land on the ground, how long do you think that is? I don't even think it's 1 second, You'd be surprised how quickly you come to rest.
2
I think maybe,
seconds.
no, I think it's like half a second maybe. Yeah, 0.7 we'll say. So,
An experiment.
yeah, we'll do that. Mo?
Yeah.
Would you like to participate in an experiment? I would say 0.7 seconds in contact with the ground. So, what's the force here, please? It's minus.
It's 635.7.
635.7 newtons.
Oh, it's 593. Sorry.
593.
Yeah.
Guys, just type the number in on the calculator. You type 445 divided by 0.7. It's not that difficult. 63.
65.7.
Okay, thank you. So the answer is, therefore, he feels. Hey, look up. He feels an up force of 635.7 newtons for 0.7 seconds.
Yeah.
That's the situation. Okay. Now next. So write that down, please. And now next section. Okay? Yeah, scrolling down. Okay, so we have this idea now. Conservation of momentum. So first I'll draw it with a picture, okay? No force. So there's no force in this box, okay? Focus up here. There's no force in this box. So here's a mass, and it's just moving around. And then here's a mass here, say M1, M2, and it's just moving around here. And then maybe there's another mass here, M3, and it's all moving around. And sometimes maybe they hit into each other. Okay? So what's the momentum in this picture? The momentum is M1, U1, if the first one is going with speed U1, plus M2, U2, plus M3, U3, etc. That is the total momentum. So let's say this is time equals 0 seconds. Now if I look at this picture again later, time equals 10 seconds. Do you think this momentum is bigger, smaller, or the same?
If there is no force.
If there's no force, if it's just closed in a box.
Same mass, same.
Yeah.
Same.
It's the same. Yeah, that's what conservation means. The total momentum is the same. Can't be that important, can it? Alright. Total momentum is the same. Sorry, that's supposed to be a picture. So let me put it down in words. If the I hope that wasn't important. Oh well. If the net, who remembers what this word net means? Total, yeah. If the net force on a system is 0, so in other words, we don't have any outside force, then the total momentum is constant. Now, you can write this down in a moment, but please note, okay, that is not the same as this situation here. What's his momentum before he hits the ground? It's this number, isn't it? And what's it afterwards? 0. Has the momentum changed? Yes. But there is an outside force on this. The ground is pushing on the man. The reaction, yeah. This situation is when there's no outside force. So there's no one pushing, there's no one pulling. It's just things moving around. Okay, that's important. So you can't use this idea for this situation. Look, see this here? What force is there? What force? Weight, gravity. You cannot use it here. Because think, what's the momentum here? 0. And what's the momentum here? No, momentum is not 0. It's because it's going faster. Yeah?
Therefore,
So therefore, this rule looks like it doesn't work. Because what did I just say the rule is? The total momentum is constant, does not change. But that's only if there's no force. Okay? If there's no force. And what is the force here? Gravity. Weight. Okay?
Questions like this hardly come up.
No, they come up a lot. So the situation they will come up with is two cars.
guns coming.
Or the guns, yeah. Because when you're moving this way, is there any gravity? No, because remember when we did our projectiles? Gravity only goes this direction. There's no gravity this way. So you can use this formula for when you have two cars that crash, or the gun with the bullet. And I'll look at some examples now. Okay? Did you write that down? That is called, it's up the top, conservation of momentum. Yep.
So constant momentum is the same as conservation of
Yeah. Conservation and constant, they mean the same thing really. Except the only thing is conservation usually means like the total for everything. Let's have a look at some examples. Okay. Do you need to write that down? Yeah. You need to go? Yeah. Okay, can I scroll down, Mo?
Yeah.
Are you sure? Okay. Example. Joshua. Come on, man. You're killing me here. Right.
It's not him.
Alright, come on, focus, people, focus. Alright, so we have our two trolleys. Not cars, trolleys. They're just rolling. There's no engine. No engine. Okay, so let's say this one here is 10 kilograms. This one here, 5 kilograms. That's going at 20 meters per second. That's going at 10 meters per second. That has a little hook. That has a little hook. And then afterwards, I know it looks stupid. 10 and 5, and they move off together. But you don't know what speed, and that's what we're going to calculate. Yes, isn't it? So what we say is this is the before collision, and then this is after collision. Before and after. Okay. So in B, what's the total momentum? The total momentum equals 10 multiply 20 plus 10 multiply 5. Yeah, so that is 250 kilogram meters per second. Can you see that? Because it's just mass multiplied velocity plus mass multiplied velocity. Yeah, I'll leave this up on the screen. Okay. After total momentum. Yeah, so in this case, what is it? What's the total? This is now one object, if you think about it. It's one. Because they're connected. So what's the mass? What's the mass? 15. And the velocity? X. So the total momentum is 15x.
It's the common velocity.
Yeah, common, yeah. But conservation of momentum means that 250 should equal 15x. Therefore, x equals, please tell me.
16.7.
16.7?
16.6666.
The 16.7
16.7.
meters per second. Okay, let's do another example. Let me see. Yes, actually, let me give you one to try. Okay, do you have that?
No.
Not yet? Okay, do you just need me to leave this piece up?
So why did you put B and A? Is that
Yeah?
is that
Before and after.
Oh.
Dana, soon, Tal. Did you write this down?
Yes.
Yes? Okay, can I go on now? Oh, hurry up. Well, what I want you to do is to do this example for me anyway, so yeah, we'll take the famous one, gun and bullet here. Yes, this is a gun. It just looked like it, yes. And then we have a bullet here. So this is before. Then after, so I'm trying my best to draw this. Afterwards, the gun is moving backwards, and then the bullet, which came out now, moves forwards. Yes, very good, yeah. Okay, so let me fill in some information for you. So we'll write mass of the gun. That equals, let's say, what would we say, 1 kilogram or 2 kilograms? And then the mass of the bullet,
0.1.
about 100 grams, isn't it? 0.1 kilograms. Now at the beginning, what's the velocity of the gun? 0. And the velocity of the bullet? 0. Then you fire. This is still the same, this is still the same. Velocity of the gun? We don't know. And velocity of the bullet, let's say it's 200 meters per second. Is that too fast? I don't know. 200.
So what did the U1 and U2 for?
Yeah, sorry, U1, that's the gun, and that's the bullet. So you have M1, M2, U1, U2, M1, M2, V1, we don't know, V2. I would like everybody for me to calculate the V1 now. So I want V1, so calculate that please, and then I'll do it. Okay, does anyone have an answer yet? Negative, yeah?
Or positive, it depends on which direction.
Yes.
X is a positive
We'll take negative, go ahead, negative 10. Exactly negative 10?
one. Exactly.
That was a total accident. Okay, so momentum before is 0 plus 0. And then the momentum afterwards would be 2v1 plus 0.1 multiply 200. So you get v1 equals minus 10 meters per second.
Why is that minus 10? I got 10, but I'm not sure.
Oh, we're having plus and minus issues again. Relax. Did you get this equation here? Then you should have gotten v1 is negative. Check your algebra.
What is that 0 plus 0?
That's the momentum before the collision. Dana soon. You're causing trouble for me. What? No?
I tried to explain it for Tanish, but I speak Korean.
Tanish doesn't speak Korean. Well, I don't know.
Me, that's me.
Yeah. Do you speak Korean, Tanish? No. Try explain it to him in English. Go ahead.
You understand that? The why?
Look, when you multiply 0, you multiply 200.
You got
constant. And then you take it to the other side, it becomes negative. And then you divide 2 by that.
You got negative 10. But I have no idea why is that 0 plus 0.
What's the 0 plus 0?
That's in the before. Before equals after.
Is that mu
Yeah.
plus m?
Yeah, if you want, it was 2 times 0 plus 0.1 times 0. Same thing. Okay, I have to move on now. Okay, next example. This symbol here, that's another symbol for impulse, okay? This means change. Change of P. So for example, this one here is change in X, I should really say. Change of X. Sorry, bad preposition. Delta X, delta P, yeah. So I don't even need to write that down if you don't want to. I'm just saying this symbol here means change. Okay? So delta P, that is mv minus mu. Okay? Right. Now, a little example here. So we're back with our rocket again. Yes?
Sorry, doesn't that mean that delta P is also the same as Ft?
Yep, you're right. Which equals I, which equals Ft. Yep. Now, and we do need to use that later. Okay. So here's our rocket again. So you might know this already, but the way rockets work is they send fuel out here very fast. And this is what makes the rocket go up. And why does that work? Well, if you think about it, let me try and draw the picture here. Before and after. Sorry. Before and then after. So here's the rocket.
So confusing, DNA.
Fine.
Yeah.
Okay. So think about it like this. There's fuel inside the tank. So what's the velocity of the rocket? It's 0 meters per second. And then the velocity of the fuel? 0 meters per second. Now, if the fuel is sent out of the back, its velocity, of course, is not 0. So let's just call it v. So then the rocket needs to move because here the momentum is 0. Let me just call this x. And let me call it... Well, I won't put any plus or minus in just yet, but there will be a minus, yeah. Let's say the rocket is m or for rocket and the fuel is mf. Okay. So what's the momentum of the fuel here? It is fuel multiply v. And what's the momentum of the rocket? M or multiply x.
Sorry, but what is
Yeah.
it? Positive?
Which one?
Why did we say plus and not?
Sorry, I should really put in the minus here. Yeah, because this one's going down. So that means MFV equals M or X. So you get X equals MF over M or times, V. So tell me, if I make the V bigger, what happens to the X? Does it get bigger or smaller? It gets bigger. If I make the mass of the fuel that's coming out bigger, what happens to the X? It's bigger. But if I make the mass of the rocket bigger, what happens to the X? Smaller. So what you want is a light rocket with lots of fuel that comes out very fast. That will make the rocket go fast. Okay? So the conservation of momentum, you can use it here in this example. And I want to talk a little bit about this. I want to talk more about this. Okay? So can you just write that down? Or draw that, and then we'll talk more about this. Did you write that down? Yep. Okay. So, this is the momentum of the fuel plus the momentum of the rocket. That should total be 0. Yeah? We're saying it should be 0 because it's 0 at the start. Now you said, Mohammed, earlier, delta P, what does that equal? FT, wasn't it?
Yeah.
So what I'll do is, delta P rocket, that will equal minus delta P fuel. And I'm going to use that formula you gave me, FT equals delta P minus fuel. So we get F, now I didn't write it in here, this is still rocket, equals minus delta P fuel over time. Now if I do this per 1 second, so per second, what's the T? Equals 1. If I do this per second. So then I get, I don't even have to do that per second, but I get the idea. F rocket. Now look, this is the change. Well, actually, I don't even have to write the per second. I'll just write in words. Please look very carefully. This is the change in momentum per time. Now, what does that equal? That's force, isn't it? But you knew that because what's this here? Force, yeah. So you get this important or useful formula. The force that the rocket has that drives it up, that's equal to the change in the momentum of the fuel per second. Okay. So if you're doing everything per second, you don't need to write the word per second. And do we normally use per second? Yeah, so we don't need to write it. So let me give you an example of this formula. Can I scroll down? Yeah, I should be able to. Okay. So let's say here, per second, I have, let's say, 80 kilograms of fuel, and it's at, let's say, 200 meters per second. This will make the rocket move up with a force. How big is the force?
80.
It's actually just 80 multiply 200. 16. Oh, and if this is, yeah, the minus just means the opposite direction.
1 more 0.
Oh, another 0. Thank you. 16 kilonewtons. So you see, this is a useful formula. If you want to know the force the rocket has going up, it's just the mass of the fuel per second multiply its speed per second. That's how much up force it has. And there's a special name for that. Does anyone know the name of this force?
Good force.
This force here has a special name. Moving force? No.
Terminal. Reactive.
Downward momentum.
Thrust. So, how would you see this question in the exam? It could be something like, a rocket burns 80 kilograms of fuel a second, and the gas released is at a speed of 200 meters per second. So I mean this stuff here. So then the question is, what is the thrust force?
What's the question? Thrust only comes up with the rockets, right?
Yeah, it's mostly used for rockets. It's the force that makes it fly up, yeah. Thrust force. Now, you can also have it in other situations, like if you're talking about a submarine under the water and it rises to the surface. But for us, it'll be rockets. I've seen this in the exam 3 times, I think, as a Section A question. You know, they'll just say, the fuel is 80, the speed of the fuel is 200, what's the thrust force? So it's just 80 multiplied 200.
That's it.
And that's it, okay? So once you know the formula or the idea, it's simple to do. Now, there's just one other change I want to make to it.
Will they actually give us an easy question like that?
Yeah, okay, I've seen that in Section A twice now, I think. 2 or 3 times. Okay. Can I scroll down? Yes? 1 sec? Okay. Yes? Now, there's only one change I want to make that makes this more realistic. I think I need to go down. Sorry, you'll have to copy it from someone. Just because I'm a bit tight on time here. So, no, let me go in black. Okay, so we have our rocket again. And coming out the back here is our fuel. So let's just say it's M, and the speed, I'll just call it, I don't know. Mass of the fuel and the speed of the fuel. Okay. But that's not realistic. I mean, it's realistic, but there's something else that's happening. Well, that's true, yeah. There's air that gets sucked in because you need the air to mix with the fuel to make the gas. Okay? So there's air that's getting sucked in. Now that's true for every engine, okay? If you think about your car, you know, at the front of the car, there's the grill, you know, at the very front of the car, and the air gets sucked in, and it's used in the engine. Okay? It's the same with the rocket. The air gets sucked in, it's used in the engine. Okay? You probably see this.
Is that used to push the floor up?
No, it's just used, like in chemistry, you know, to make it explode, to make it burn. You need some oxygen with the fuel, you mix it together, and you burn it and release it. Okay? If you think about an airplane, you know, jet airplane, the big engine, it sucks in air and fires it out the back. Now, it's not the same because this also has actual fire, okay? But what I'm saying is for all engines, they suck in air. Now tell me, do you think this helps the rocket move or does not help it move? Both. Good answer. But no, I need one. Helps or does not help?
No.
Well, think about it. What direction is the air moving? Down. And what direction is the fuel moving? No, the fuel. Down. So, in fact, it helps the rocket, it gives it more force. Because if there's more momentum here, there must be more momentum this way. Okay? So, if you had the air as well, so let's say the air is, let's just say it's MA with UA. So, for example, 10 kilograms per second is sucked in at a speed of 20 meters per second, or whatever. And Joshua, you said there's one force I left out here. What's that? Gravity. There's a gravity here. How big is that? M or G. Yeah?
About there is also fuel.
Oh yeah, so we're going to work out the total force here. So, total force now. What is the total force? So what's the force going up? There are actually two. There's...
What about their friction?
Oh yeah, friction. Let's forget about friction. No, should we forget about friction? Yeah, you'll never get friction in the exam for this, but if you want... Okay, friction. Okay.
And the weight is not just the mass of rocket, it's also the mass of fuel.
Yeah, but the fuel will be... Okay, so when I say M or, I mean the total M, the whole thing. Use a different letter? No, I'll just leave it M or. I'll just use M or, you can write it down, total mass. So, going up, there's the force of from the fuel. What's that? M, F, U, F. And then there's the air. What's the force from the air? M, A, U, A. But then I have a minus M or G and minus friction. Yeah. No, not mu r, just friction here.
So what's MRG?
The weight. Yeah. And vocabulary check. What do we call this force here that makes it go up? Thrust. And then what do we call the force that slows it down? We call that the drag. This, remember, is the drive. And this is the drag. It slows it down. In the exam, though, we usually don't have this and usually don't have this. In the exam, they usually just do this one minus this one, okay? In the exam. But I'm saying, if there was the air being sucked in, it just is an extra force to help it go up. That's all. So it's not too complicated. So there you go. Rocket science. Not too complicated. Okay, let's have a look at questions here. So, yes, as well as highlight our challenge sheets. Okay. So 11, but not the whole thing. 11A, B. Listen and write, circle these.
A and B.
Page 52.
So what is MA?
That is the force that the rocket gets from sucking in air. So, for example, MA is the mass of the air sucked in per second, and the UA is how fast the air is being sucked in per second. Okay? So if I think about a car engine, a car probably sucks in like a kilogram of air per second, something small. And then it's not that fast, maybe 1 meter per second, So 1 kilogram multiplied by 1, how big is that? 1. Yeah. So the car gets an extra 1 Newton of force driving it because it's sucking in the air. But it's nothing. Where does most of the force come from for the car? The engine, the wheels turning, But you still get a little bit of force from the air being sucked in the front.
So physics page 2.
Yes, 52. So 11A and B.
Enough.
No, be quiet, Tom. You be quiet. 12 A and B. 13 A1. Oh, do we do kinetic energy? I don't remember if we did that. No, we did. B, 13B.
A1 and B.
Come on, we'll have
A1.
a lesson tomorrow.
Shh, Todd, you're making it worse. 13A1 and B and C. C both parts. C1 and 2. Okay. Great.
So 13 is the whole like A and B.
Yes. 13. No.
A1
A1. Yes. Yeah.
and B and C.
Okay. 14.
Is it the whole of 40?
It sure is. Yeah. 15. I promised you last time I'd give you more homework next time to make up for it. 16.
So like 14 is like A and B.
Yeah, everything in 14 is wrong.
And B1, B2.
It's more than you gave us for weekends.
I know. So you'll have to work hard.
Do we have to do 15?
Get 15 and 16.
You can bring your thoughts, it's fine.
Sorry, I believe that you have no heart.
You believe wrongly.
I'm looking for like
And one more, 17.
When are we supposed to submit it? Anymore?
Tomorrow. Yes, tomorrow. And I'll check the homework from yesterday, the one you were supposed to have today. I'll check it tomorrow. So some people missed 7 and 8. So you should have that in your notes as well, okay?
Yes.
Now look, it needs to be this, but we're nearly finished this chapter. There's only 1 page of questions left to do. And then once we have the chapter finished, then we have
Progress.
half of this book finished. Okay? There's 6, yeah. But this one is the biggest of the 6.
Oh, okay.
Okay? Yeah.
So it's the hardest.
It's the hardest and the biggest of the 6.
No,
So
it's
like
not
this book here is about 5
Don't forget
weeks.
about
Hey, this book is 5 weeks. The next book, shh. Just because I'm your teacher doesn't mean I won't come down there and slap you. Yeah. This book here is 5 weeks. The next book is 2 weeks, and the next book is 2 weeks. Okay. So this is actually half of the semester. Okay. So it's hard work. Yes.
We're not taking off this, right?
No. Well, I mean, a tiny bit. Snell's law. That's really it. But there's no lenses or anything like that. All right. I'll check this tomorrow then.
From yesterday.
Yeah.
Now we have.
There's no time for me to chat now. No time.
Now we have a.
Yes, you love it.
Let's check.